An inductor is an element, also a passive element, that stores energy in the form of a magnetic field. I do want to add, one thing that was omitted by your textbook in the capacitor discussion is that capacitors store energy in the form of an electric field. So there's an electric field that exists between the plates of the capacitance, and that's how energy is stored. And we express that, of course, you remember energy stored in a capacitor is 1/2 CV squared because voltages are related to electric fields. In an inductor, the energy is stored in a magnetic field. The primary application that you will see as an undergraduate in any electrical engineering department that you see every day is that of a transformer. So these are, as you know, everywhere. They're along the street in the power system, the power distribution system. You also see inductors in electric motors. You do see some inductors in power supplies, and some of the more conventional analog versions of radar, TV, radios, and even some of the digital ones. So all conductors will have inductance. So if you go out on the street and you see power lines, forget about the transformers, just think about the power lines. In between those power lines, there's some inductance associated with that. So it's not so much that the conductor has inductance, it's that the enclosing of an area by a conductor, no matter how large the area and how small the conductor, that's going to be a finite amount of inductance. Now, that's greatly enhanced when you coil it up. So here are some pictures of different inductors. This is one that obviously is just handmade coil. Both of these. This one is a packaged inductor. With inductors, it's fairly easy to make your own. I do want to make one comment. In this class, we are dealing with inductors that are linear elements. So what's pictured here, if you look kind of in here, that's a magnetic core. Inductors wound around magnetic cores are done so for some really good reasons, but as soon as you do that, your inductor and its behavior becomes nonlinear because you've introduced a magnetic energy storage material. So inductors are very different from capacitors in that capacitors, you have a ton of different kinds of dielectric materials, almost all of which can be modeled very, very close to air. In other words, they're linear. So you double dV/dt, you'll double the current, and so on. Inductors, that's not the case. So there's not like a bunch of different kinds of materials that you can stick in here to get linear behavior of the inductor. In fact, the introduction of a magnetic material limits the range to a very narrow range or a very small range typically over which you'll get linear behavior. Furthermore, when we start to talk about AC circuits, as soon as you introduce a magnetic core in here, its behavior varies with frequency as well. So the main difference between inductors and capacitors as far as you're concerned in this class is the inductors that we'll work with are linear, which means they would have to have an air core or a very, very limited operating range. All right, the relationship between the voltage and the current in the inductor is the opposite from what it is in the capacitor. This is also an equation that comes from electromagnetic field theory. It's a circuit's analogy of Ampere's law and Faraday's law. So V is L di/dt. L is the unit of inductance. It's measured in henries. 1 henry is a volt second per amp. Unlike capacitance, we don't have anything analogous to Q is equal to CV. In inductors, why not? Because in the magnetics world, we don't have any single unit of magnet. So magnetics are always bipolar. We always have a north pole and a south pole. We don't have anything that's analogous to Q. There's nothing that would be like a single magnetic monopole. So because of that, the equation for inductance, this is it. So same kinds of things apply here. Notice that if the current is constant, di dt will be 0. So the voltage across an inductor is 0 if the current is constant, meaning that the inductor looks like a short under DC conditions. The other thing about inductors, similar to what we discussed before, is if the current tries to change instantaneously in an inductor, it will drive the voltage to a very high value. In fact, an instantaneous change in di dt would drive the voltage to infinity. An instantaneous change in I would give you infinity for di dt, driving the voltage to infinity, which is unphysical in a real-world circuit. So you do not have instantaneous changes in the current in inductors. So the voltage developed tends to oppose the changing flow of current. That comes from physics. You may have done some stuff with Lenz's law and Faraday's law where you looked at the right-hand rule and you looked at how to determine how the voltage changes. In circuits, we have some sort of systematic ways to deal with that make it a little bit less ambiguous, and you don't have to do all kinds of weird gyrations with your right hand to figure out the right hand rule. So this statement is here primarily just as a reminder that what we are going to do in circuits is consistent with what you learned in physics. So the inductance of a solenoid. So this is a solenoid. It's got a defined length. It's got a core material that has permeability mu. For now, we're just going to go with that, even though I told you that in reality, magnetic materials are highly nonlinear, but we'll go with it for now. If you calculate the inductance there, L is N squared mu A over L. For air, mu becomes mu naught, which is a constant. N is the number of turns, so in other words, the number of times the wire's wrapped around the core. The cross-sectional area is A, the length is L. Now, why would you want to use a core? Because even if this coil is very tightly wound and the wires literally lay right against each other, there's still a little place here in between the windings where a magnetic field can leak out. And so what that does is that diminishes the value of the inductance because you're not keeping all of your field in this solenoid. So in reality, this equation is an approximation that is only as good as how tightly wound your coil is. And no coil is perfect, so this is never a perfect equation. The analogous situation in a capacitor is that at the edges of the capacitor you get what is known as a field fringing effect, meaning the electric field is not uniform at the edges. In physics, you generally tend to ignore that. We ignore that a lot in electrical engineering as well, but it is a thing. And so it's what gives you the difference between an inductor or a capacitor built in the real world and one that you model in a circuits class. So the current voltage relationship for an inductor, if you take that differential equation 2 slides back, and you integrate both sides of this equation, then you'll get basically an equation for the current. So if you're given an inductor voltage and you want to solve for the current, it is essential that you know the initial condition on the current. Usually T naught is time equals 0, but it could be any starting time at which you have a defined initial condition on your current. So inductors and capacitors have both a differential equation or a derivative equation and an integral equation depending on what your unknown is. So if your unknown is the current and you're given the voltage and the initial condition, this is the equation you would use. Okay, we do a similar thing with power that we did with capacitance. Power is V times I. V is L di dt, so we substitute that, and then to get the stored energy, we integrate the power, and we get 1/2 Li squared. So once again, inductors have some properties. If the current through an inductor is constant, it has a voltage of 0. So in DC, an inductor looks like a short. Also, we said the current through an inductor cannot change instantaneously. If it did, the voltage across the inductor would be infinity. And that is an important consideration. If you turn an inductor off abruptly, it will produce a very high voltage. So that can kill you. It can also be used in things like pulse power applications if you are intentionally trying to generate a high voltage and you can figure out how to disrupt the current in an inductor abruptly, like you blow up the rest of the circuit, then you can produce a very high voltage very quickly. So like the ideal capacitor, the ideal inductor doesn't dissipate any energy that's stored in it. You can get the energy out later to the circuit. In reality, the inductors do have internal resistance because they are made from a wire. And of course, you did a few little calculations in a previous project with the strain gauge and determined that, wires do have resistance. So a real inductor will have a winding resistance, and that'll be in series. It'll be modeled as being in series with the inductor. Also, because you have these wires laid on top of each other, you have what's referred to as a little winding capacitance. And this can be modeled in various ways. They're usually very small, and at normal operating frequencies, they're not an issue. However, when frequencies get very, very high, then suddenly your capacitance, the winding capacitance, can make a significant difference. When currents get very large, the winding resistance can make a significant difference. So these ideal properties of really both inductors and capacitors can be applied under most normal operating conditions. But when you try to push the limits of the physical world, then suddenly these non-ideal effects can become significant. All right, well, inductors, because V is proportional to the derivative of current, they're going to combine in a way like how resistors will combine. So I won't go through the loop and node thing again, but basically in inductors, if you have a bunch of inductors in series like what's shown here, they combine to a single inductor by adding. So right here, the equivalent inductance is the sum of all of the inductors in series. They behave just like resistors. The same is true if you have a bunch of inductors in parallel. They're going to combine like resistors there as well. We can prove that using KCL, but I'll just show you the result. That 1 over the equivalent inductance is the sum of the inverses of the individual inductors. So the parallel combination resembles that of resistors. As a related note, you can apply a delta Y transformation to inductors and capacitors. You let the capacitors go to 1 over C before you use the formula. We are going to talk about that a little bit in circuits 2 when we talk about three-phase power, and we'll look at how to do a delta to Y transformation when you have typically it is inductors that you're working with, but it can be capacitors. There are ways to handle that, so I'll just leave the book's point here and not really comment on it further. All right, so this is a very nice summary chart of capacitors and inductors. It shows you the various relevant formulas that you can use to do the calculations. And so what we're going to focus on when we look at this chapter as far as problems go, we're going to focus on the application of the VI relationships for capacitors and inductors. So in other words, if I give you a capacitor voltage, then I would expect you to know how to calculate the capacitor current. If I give you an inductor voltage, you would need to know to apply this formula to calculate the inductor current. You need to know how to determine the stored energy, how to do a series parallel combination, that at DC the capacitor voltage or the capacitor looks like an open circuit, the inductor looks like a short circuit. And in a capacitor, you can't change the voltage instantaneously. In an inductor, you can't change the current instantaneously. If you forget that, you can go back and look at the formulas and look at what you're taking the derivative of and let the mathematics guide you there for these last two properties. But very important table. Highly recommend that you print this out and keep it in front of you when doing homework problems. So in the final video, we'll look at a couple of kind of unique and special circuits, and then we'll make you some videos on walking through some example problems with you before you do the homework.